Hi, this is Professor Fernandez. This is video 2 in lesson 6. In this video, we're still talking about evaluating limits. Now we're going to switch though to algebraic techniques. So I'll do 2 examples from Calculus Simplified to help you get used to these new ways to evaluate limits. So let's look at the first one here. I'll zoom in a little bit. It says evaluate the limit as x goes to 3 of x squared minus 9 over x minus 3. Great, so at this point in the course, we've talked about a few possible ways you could evaluate the limits. I'll just review some of them quickly. You could graph this function and see if you can get some information from the graph about what you think the limit might be. You might, then want to confirm that through some technique, like one of the ones we're about to talk about. You could draw a table of values. You could pick an x value and then try to pick numbers that are close to, for example, 3. From above and from below, or from the left and from the right, and then see if there are values that the function is tending to. If it's the same value, then this two-sided limit exists. You could also try, for example, to use the limit laws like we did in the previous video. So the video 6.1 talked about the limit laws. The limit laws are not going to work here, though, and it's a great way to just review that, but also give you a sense for why we can't just substitute in x equals 3. And you'll see why in a minute. First, the denominator as x goes to 3, x minus 3 goes to 0. So that already is a tip-off that we can't do this. We can't use the limit law that says that the limit of a quotient is the quotient of the limits because the denominator is 0. And if you go back and look at the limit laws, this is theorem 2.6 in the textbook, Calculus Simplified. One of the presumptions for using the limit laws when you are evaluating the limit of a quotient is that the denominator limit is not 0. All right, so all of that said, right, what do we actually do? What can help us evaluate this limit? Well, you might have already seen a possible way out, right? And it has to do with this function. Because if we look closely, x squared minus 9, this should remind you of a difference of squares because 9 is 3 squared. And so long story short, we can factor this, right? What does this factor into? Well, x minus 3 and x plus 3. And we can always double check that, right? This would be x squared plus 3x minus 3x and then minus 9. Right? These cancel out, so I'm left with x squared minus 9, which is what I started off with. So great, check, that all works out. All right, so now that we have a factored form, we can then go back to the function itself and say, oh, wait a second, so x squared minus 9 over x minus 3 is x minus 3 times x plus 3 over x minus 3. And we can start canceling. So we can simplify this function. So one of these x minus 3's cancels, right? And at this point, it's good to remind yourself that actually this does not equal just x plus 3. Okay, this is a common misunderstanding that I talk about in this section in the textbook. This function is not defined at x equals 3, right? That's not in the domain of the function because the denominator is 0 there. This function is defined at x equals 3. Its value is 6. So you can't have a function that's not defined at x equals 3 equal a function that is defined at x equals 3, right? That's a contradiction. So what happened here? Well, to fix this, we would say, this function equals this function so long as x is not equal to 3, right? That's the way that you would fix this. But, in fact, we're not really interested in being that precise because remember that we're taking the limit as x approaches 3. So actually, we don't care what happens at x equals 3. So the better way to say all this is to say that the limit as x goes to 3 of our function is equal to the limit as x goes to 3 of x plus 3. See, in doing that, we don't have to reference what happens at x equals 3 because the limit approaches indefinitely but never arrives, right? It doesn't matter what happens at x equals 3. So then we continue on from here, and now we could use a limit law if we wanted to, or we could just view this as x is approaching 3. This function is x plus 3, so I should be approaching 3 plus 3, which is 6. And that is our answer for this limit. Okay, great. So let me move over then now and talk about this next example, 2.28, and then show you a different algebraic technique. So the algebraic technique we just talked about here was factoring. So that is one thing that you can definitely use. We're doing it over here, right? Right there specifically. One thing you can definitely use to help you evaluate limits algebraically. Let's talk about another technique here. So we are going to use, in this case, rationalization. Okay, just a quick little, recap, right? Let's say you have 1 over square root of 2, and you want to get the square root of 2 out of the denominator. Well, you multiply by square root of 2 over square root of 2, and that makes it square root of 2 over 2. So there we go. No more radical in the denominator. A similar thing happens with functions, except that you can multiply by something called a conjugate. So let's say if you had 1 over 1 plus square root of x, what if I want to remove that square root of x from the denominator? I multiply by the conjugate. So that's these two things with the sign between them changed. So there's the conjugate. And what would I get? I would get 1 times 1, that's 1. 1 times negative root x plus root x times 1. And then minus root x times root x minus x. And you can see that after doing that calculation, I would end up with a fraction that does not have a radical in the denominator. Right? So again, I've gotten rid of the radical that was originally there. So I've rationalized the expression. So we're going to do a very similar thing here for this limit example. So let's take a look at the function itself. So the function is x over square root of x times x plus 1. As always, my suggestion is to just try to substitute in the point. Maybe this function right here is continuous, and therefore its limit equals the value of the function at the point. So let's try that. So if I put in 0, square root of 0, 0 plus 1, the numerator is fine, the part in the parentheses is fine, but this part is not. So I have a 0 in the denominator. The square root of 0 is 0. So I can't do that. I can't just substitute in x equals 0. So I have to do something else. There's no factoring that I can do here. So this is why this problem requires a different algebraic technique. This is the rationalization. It's really a straightforward rationalization in this context. And we can even avoid the rationalization, as I'll show you in a minute. But anyway, here is the square root of x. To get rid of it, we would multiply it by multiply top and bottom by square root of x. So let's do that. Square root of x, square root of x. Okay, and then in the denominator, these square root of x's give me x, and the x plus 1 goes along for the ride. In the numerator, I have x square root of x. Great, and then again, I can cancel these two to give me x square root of x over x plus 1. Like I talked about with the example over here, remember, there's a little bit of a technicality. I should put here x not equal to 0, because again, at x equals 0, this function is perfectly defined. It's 0 over 1, which is 0. At x equals 0, the original function is not defined because there's a 0 in the denominator. So that's why I have this technicality here. But as I said over there, we really don't need all this technicality, because what we have just shown is that the limit of the original function, here we go, is equal to the limit of this new function. That is a true statement that is not requiring this technicality as a qualification, because again, the limit does not care what happens at the point, right? It's all about approaching and never arriving. All right, and then from here on, we can continue and try again to substitute in x equals 0, see if we get our limit answer. And in this case, we do. The square root of 0 is 0. The denominator is 1, so our limit is 0. Great, so last thing to end the video, I mentioned that you don't have to do rationalization here. How could you have avoided that? Well, if you look at this function, you could just focus on this part of the function. And you could say, hey, x divided by square root of x is square root of x, right? I can cancel out a square root of x from that's contained in x, right? You can think of x as square root of x times square root of x. Again, I just, because I'm a math professor and I want to make sure, that things are correct mathematically, we would add the caveat here, x, not equal to 0, because again, this is defined at x equals 0, this is not. But the point of that little calculation was to show you that, this, we got to the same function that we ended up with up here using rationalization, but down here we did not use rationalization. So in a sense, this is kind of a third technique that I've unearthed from this example, which is just simplification, right? If you can simplify the function you're working with, that in and of itself might help you evaluate the limit.